All right, so the key themes in Unit 3 in the physics unit, okay, were basically movement and energy. Those were the key themes, okay? When we're talking about energy, we're talking about types of energy, we're talking about thermodynamics, we're talking about systems, okay? Work energy theorem, conservation of energy, and efficiency. Those would all be the things kind of tied up in the energy theme of this unit. Okay? Within the movement theme of this unit would be things like scalar and vector quantities. Okay? V equals d over t, acceleration, graphing, stuff like that. Right? And to an extent, work energy theorem and conservation of energy also have movement components to them. Okay? That's why they were at the end. They were kind of a combination of both. Right? So those are the two themes in the unit and the kind of items that go in with them. The first thing we specifically talked about in this unit, okay, types of energy. That will be in the multiple choice. Okay? You had an example of this on your unit exam. One of the multiple choice questions was something like, the energy in a rolling bowling ball would be best described as A, chemical, B, nuclear, C, mechanical, or D, magical. I can't think of the fourth one. Okay, something like that. Okay, you'd have your forms of energy to be able to recognize it. Okay, so general recognition, recognize the types of energy right from there. Okay, and then thermodynamics. You definitely need to know the laws of thermodynamics. Because the laws of thermodynamics don't just apply in this unit, they also apply in Unit 4, especially the second law. So the first law of thermodynamics tells us what? Something about the nature of energy. Can we take a put up, please? Energy can't be created, it can't be destroyed. It can be changed if you do work or if you add heat. Okay, all of that kind of stuff. That's the law of conservation of energy. That is the first law of thermodynamics. The second law of thermodynamics, energy flows, hot to cold, high to low. Okay, so those are the two laws that you definitely need to know, okay, and be able to apply to different situations. Okay, and that second law is a big part of climate and energy transfers on a global scale, so it comes up again. Okay. We also talked in thermodynamics about how heat engines work. Okay, a heat engine harnesses the second law of thermodynamics, knowing that energy is going to flow from high to low. If we put something in between the high and the low, then as energy and matter flow through it on their way to obey the second law, we can harness that to do work. We also talked about heat pumps, like your air conditioner or refrigerator, okay, and how they go against the second law of thermodynamics by using energy to push heat from a cold area to a hot area. Okay. And that was part of the reason why you had that multiple choice question on your last unit exam about what would be the most efficient way to cool your house. Do you want your windows and blinds open? Do you want your windows and blinds closed? Okay, all of that kind of stuff. Okay, that was kind of an application multiple choice question about the second law of thermodynamics. So expect probably something like that. Okay, also something that's not on here, but we do need to know the systems. Okay, open, closed, and isolated. Right, again, be able to recognize them. It would be a multiple choice question. So an open system exchanges matter and energy with its surroundings. A closed system exchanges only energy with its surroundings, and an isolated system exchanges neither one. Okay. All right, so that's how we started the unit, just an introduction to energy, what it is, all that kind of stuff. There's like, I think 2 multiple choice questions that involve people, but they're obvious, okay? Like they're really obvious. So just make sure you go over your notes about the types of energy, you know, and I'm not gonna ask like about some obscure person like Joseph Black or something like that. I'm not gonna ask about somebody obscure, it'll be somebody that's obvious, okay? All right, scalar and vector quantities. All right, so you definitely need to know which things are scalar, which things are vector. You could possibly have a multiple choice question that says which of the following are scalar quantities. Okay, something like that. You know, that would be, you know, certainly game. But the biggest place where knowing what's scalar and what's vector is in the written response. If you recall, on your physics exam, almost no one remembered to put a vector on the final velocity they calculated in the acceleration problem. Okay, that's exactly what I mean. That's a place in the written response where you need to know what's vector and what's scalar. If you're asked to calculate speed, that's a scalar quantity. You don't have to put a direction on it. You're asked to calculate velocity, that is a vector quantity, and it needs to have a vector on it. Okay, so that's kind of where that's important. It also makes a difference if you're looking at a graph. Okay, if I give you a position versus time graph and say calculate the total distance, you calculate that differently than you would if I asked you to calculate the total displacement, because one's vector and one's scalar. One direction matters, the other it doesn't. Okay, so that's kind of the places where needing to know scalars and vectors would come into play. That day we also talked about the 2 forms of V equals d over t. Okay, so we talked about this one, okay, where we're talking about velocity equals displacement divided by time, which can also be written like this, final position minus initial position divided by time. That's how you calculate it on a graph as well. Okay, whereas this one is speed equals distance over time. Okay, so we calculate distance on a graph by adding all the sections. So where are you going to have to use V equals d over t? There's one multiple choice question about a simple V equals d over t calculation. Super simple. Okay. There are no V equals d over t problems in the written response. Right, and also remember here, displacement, I wrote it up here, but displacement is calculated final position minus initial position. You don't have to memorize that formula, it's on your formula sheet, okay? It's just something that, oh, right, I have to calculate displacement. How do I do that? Okay, what does it look like on a graph? Well, I find where the final position is, I subtract where the initial position is, just stuff like that. Okay, and then acceleration, there is a written response problem. I told you that yesterday, okay, on acceleration. So using A equals VF minus VI over T. Expect you'll probably have to manipulate that. On your unit exam, you had to solve for VF. Okay. Should you also know what acceleration is? Like, could I have some multiple choice questions about the nature of acceleration? Okay. Yeah, definitely. Okay, so make sure you just understand what it is. Okay. Probably also, because it's going to be related to the next point, how to recognize when it's happening on different types of graphs. Okay. How do I know if an object is accelerating on a position versus time graph? What will it look like? It'll be what? Not on a position time, on a velocity time there'll be a slant. What will it look like on a position time? It's curved, right? Because the amount of distance traveled every time interval is increasing because it's going faster. So it gives us a curve. So things like that, okay? Be able to recognize and understand, again, that's kind of the nature of acceleration. Okay, then graphing, okay? Be able to read and interpret, okay? A little bit of extrapolation. Graphing was a huge part of your unit exam. It is much less so on the final. Okay, reading and interpreting is probably the biggest part of graphing on the final. As I told you yesterday, the graphing question in the written response involves no calculations. It just is interpreted. Okay, and what I mean by interpreting is I give you a graph, maybe it's got a few sections, and I ask you, describe the motion in each section of the graph. So maybe I show you a graph and it looks like this. So it's a, let's say it's a position versus time graph. Okay. All right, what's the object doing? Let's say that's part A, that's part B, that's part C. What's the object doing in part A? Okay. I would say I'd probably be looking for a little bit more specific type of an answer. It is moving, okay, but I'd be looking for in what way is it moving, maybe even what direction is it moving, okay, something like that. So this object's moving, it's moving, is it accelerating or moving at a constant velocity? It's moving at a constant velocity in a forward or positive direction. Right? That would be the kind of answer I'd be looking for. That says I totally understand what's going on. You say moving, yeah, that's, you know, yes it is, but what else? All right, what's happening in part B? That's flat, by the way, it's supposed to look flat. No change, yeah, its position is not changing. Okay? It is sitting still, would also be acceptable as an answer. There's not much more specific you can be when nothing's happening. Okay, and what's happening in part C? It's not reducing speed. Nope, same thing. Going backwards at a constant velocity. Remember, acceleration on a position versus time graph looks like this or looks like this. Okay, it's curved, right? If it's curved, then it's accelerating because the distance traveled is changing every second rather than the same amount of distance traveled every second. This is showing the same amount of distance traveled every second. That means it's traveling at a constant velocity. Right? So that's what I'd be looking for, something like that. Or you could have a velocity versus time graph as well. Right? And maybe it would look like this. Okay. So this is meters per second. This would be seconds. What's it doing in part A? Velocity versus time graph, and that part's flat. What is that saying about the velocity? It's not changing. So in other words, it's traveling at a constant velocity, and it's positive, right? Because it's above zero, right? This would be zero right here. All right, what's it doing in part B? Is the velocity changing? What do we call that? It's accelerating, right? Okay. Which direction is it accelerating? Negatively. Okay. That's all you have to do. You have to just analyze the graph, look at it, and go, okay, what's happening here? This is a velocity versus time graph, and because this line is slanted, that means that the velocity is changing. Change in velocity is acceleration. This is acceleration. Okay. You don't have to memorize it. Just talk it through. Okay. Obviously in your head. Don't talk it through out loud on the test. All right, and then for part C, okay, again, it's a horizontal line, so now it's not accelerating, it's traveling at a constant velocity, but which way is it going now? Backwards, because now it's below zero, right? Its velocity is now negative. Right? And maybe on the graph, maybe even it would have, you know, that it's -6 and this was +5. You could even say it's traveling at a constant velocity of +5 meters per second, or constant velocity of -6 meters per second. Okay? You could be that specific. All right? Does that sort of make sense? Okay. So extrapolating, there's just a tiny bit of that. Okay, the stuff that's in the multiple choice, and I think I told you yesterday, there's 4 graphing questions in the multiple choice. I think it was 4. Okay, and they all involve, here's a picture of a graph. Tell me something about it, or make a simple calculation about it. Oh, and then I got all this stuff in here about graphing, which is what we already talked about, and I drew it all for nothing. Okay, so yeah, that's all the stuff that we've already talked about there. Okay, so for calculating distance, remember you add all the sections together. So if this was a position versus time graph, add, and you get your total distance traveled. Okay, whereas for displacement, it would be this position here minus that position there. That would give me my total displacement. Okay, if I'm finding displacement on a velocity versus time graph, okay, then I've got to find that area underneath the line. Okay, look at all the shapes, okay, that kind of stuff. Again, there's not nearly as much graphing. Was there 9 marks on the whole test on graphing? Okay, whereas on your unit exam, it was a quarter of the test. Okay, so it's not nearly as big a part of it as on the final exam. Okay, and then when we do velocity versus time graphs, okay, that's what we were just talking about. Okay, acceleration shows a change. Anytime there's a change in velocity, it's accelerating. Okay, remember that the slope of the line represents the acceleration, because when we manipulate it, okay, y minus b over x is actually final velocity minus initial velocity over time. Okay, so that's how we would do that. And then displacement is the area under the line, okay, which we just talked about a second ago. Okay, so if I had this graph here, I would find all the areas and add them all together. Ringing a bell? You don't have to do much of that. I'm just telling you, okay, but you don't have to do much of that. It's mostly read and interpret. There's very little calculating. And I've already told you, the written response contains no calculation. So you're looking at 4 marks in the multiple choice on graphing. If there's a calculation for 1 mark, it's going to be pretty simple. I would not ask you to do this for 1 mark. Okay? Everybody with me on that? How much time do you need to spend studying this? Not very much. Okay? Not something I'm going to ask you to do on the final. Read, interpret, simple calculations. All right, then work energy theorem, probably the most important concept in the whole unit. Expect you're going to have a problem. I think I told you that yesterday. You're going to have a problem on work energy theorem. Okay, so work energy theorem says that work is a change in energy. For us in Science 10, that's going to mean either potential or kinetic energy. Okay, it'll be one or the other, which usually meant that at some point we had this happening. Force times distance equaled 1/2 mvf squared minus 1/2 mvi squared, or we had force times distance equaled mghf minus mghi, okay, something along those lines. Work is a change in energy, okay? That's what we're saying when we write that stuff. Okay? Is that the work, the force times the distance equaled, okay, the change in energy. Your biggest challenge on one of those problems is to determine whether it's potential energy that's changing or kinetic energy that's changing. If the object's height is changing in the question, so the object's being lifted, what type of energy is changing? Potential. If the object is having its speed changed, either faster or slower, then we're looking at a change in kinetic energy. Okay, that's how you identify, that's how you get to this step here. Okay, you figure out what's going on in the question, determine what type of energy is changing, and set it up. Okay, we did a lot of those in class. Okay, so there's some understanding stuff, okay, in the multiple choice, just a few things about work energy theorem, but obviously there's written response, okay, because I told you that yesterday. So just remembering these things, potential energy is mass times gravity times height, okay, and kinetic is 1/2 mv squared. Some of the multiple choice do talk about that. They don't ask you to do any calculating, they just ask things like, you know, which of the following affects the potential energy of an object, okay, or which doesn't affect the potential energy of an object. Any questions so far? And then after that, we did conservation of mechanical energy. So that's the roller coaster questions, or a sled going down a hill question, or somebody jumping out of a plane question. Okay. The difference between those two, in a conservation of energy question, there's no change in energy. Okay. Energy at the beginning or top of the hill is equal to the energy at the bottom of the hill. In a work energy theorem question, the energy is different at the two positions. That's why we subtract them and look for the change. Okay, something that we struggled with a little bit on the unit exam was telling the difference between a work energy theorem question and a conservation of energy question. Okay? Here's how you tell the difference. There is one thing that will never be in a conservation of energy problem, but is always part of a work energy theorem problem. What is it? Force. Okay? If a question asks you to calculate force or gives you a force, it's a work energy theorem question. Because force is never part of conservation of energy, because if there is a force other than gravity, work is being done, and the energy at the beginning will not equal the energy at the end. Okay? In a conservation of energy question, all that's happening is gravitational potential energy is getting turned into kinetic. There's no change in total mechanical energy. Okay? That's how you tell them apart. Right. Try this one. Okay, so we got this box sliding down a hill. Okay, the hill is 20 meters tall, and at the top of the hill, the box is moving at 4 meters per second. The bottom of the hill, sorry, not at the bottom of the hill, nearer the bottom of the hill, it's moving at 10 meters per second. I want you to figure out how far above the bottom of the hill it is in the second position. Okay, give you a few minutes to try that one on your own, and then we'll walk through it together. So the first thing is that the energy here at the top, the initial energy, is equal to the energy there on the second point that's just a little bit above the bottom, the final mechanical energy. Right, how do we calculate mechanical energy? Well, it's the potential plus the kinetic energy of an object at any point. Right, so here we do have potential because it's 20 meters off the ground. Okay, so there's potential energy here, and it's moving at 4 meters per second, so it's got kinetic energy as well. So initially there's EK initial and there's EP initial. Right, at the end there's definitely kinetic energy final, and if they're asking us to calculate the height, there's probably potential energy at the end as well. All right, so all four types of energy are present in this question. All right, so we're going to have the initial potential plus the initial kinetic equals the final potential plus the final kinetic, and what we're looking for is part of the final potential. So we just want to get that by itself by subtracting EKF over to the other side. All right, so we're going to have EP initial plus EK initial minus EK final equals EP final. Then we can plug in our formulas. Okay, so we'll have this m times g times h initial plus 1/2 mv initial squared minus 1/2 mv final squared equals mgh final. Okay, we can cancel off all the m's because they're in every term, and then we just have to divide both sides by g in order to get the final height by itself. Right, then our next step is plug in all the numbers. Right, so 9.81 times 20, that's the initial height, plus 1/2 times 4 squared, the initial velocity, minus 1/2 times 10 squared, the final, divided by 9.81. Our final height's 15.7 meters. Right, so it's not a very tall hill. Or they haven't gone down very much of it. What's that? No.
Not the angle we showed the triangle.
No, definitely not. Well, I mean, it could still be, it's just they didn't go down very far, right? They're still 15.7 meters above the bottom of the hill. It's still a 20-meter hill. They just haven't gone very far down yet. All right, questions on how that worked? Okay, and we said there's going to be a roller coaster question on your final exam, so this is exactly how that works. Okay. All right, and then the last thing we went over was efficiency. Okay, there's some multiple choice. There's 2 questions. They both involve using the formula. Okay, so on our formula, we have the actual efficiency equals the actual work divided by the input. Okay, and that'll give you your decimal, 0.87, 87%. Okay, 0.32, 32%. Right, that formula is again on your formula sheet. It's not something you have to memorize. Okay, and it's 2 marks in the multiple choice. And as I recall, you could probably figure out what the correct answer was without actually punching it into your calculator. Okay, if the calculations are that simple / obvious. All right, that's what's on there. Now, yesterday we went over the exam in detail, so you already know, okay, how many of each type of question and the weightings and all of that. So, do you guys have any questions you want to ask, or anything you want me to go over in more detail or demonstrate from physics or any of the units? Because we didn't really get a chance to do that for chemistry. Well, we sort of did. We didn't get much. I also have your unit exams laid out. Okay, if you would like to have a look at any of your unit exams, all I ask is that before you grab your unit exam, you deposit your phone in here. Okay, so if you want to look at any of your old tests, okay, just put your phone in the box and then come see me, and I will grab your test from the pile and give it to you. If you're not going to do that, then you have a final exam review package that I posted last week that you could be going over, notes you could be studying, and I am happy to answer as many questions as you can come up with until the end of class today. Okay, so guys, just had a request here for a quick work energy theorem example. Okay, so this question is asking what force is used. So right away, that's work energy theorem. We know it's not the conservation of energy because it's asking us to calculate force. Okay, to throw a ball over a 1.5 meter distance, okay, to a height of 21 meters. Where do I have to assume it was thrown from? A height of 0, right, ground level. Okay. All right, so what kind of energy is being changed here?
No.
Potential, right? Change in height. All right, so that's going to mean force times distance equals m times g times h final. minus 0, because my initial potential energy is nothing. I don't have any on the ground, right? I'm just manipulating to find the force, so I divide by d, okay? And then I plug in my numbers. So force will be, didn't tell me the mass though, 1.5 kilograms. Okay, so 1.5 times 9.81 times the final height, 21 meters, divided by 1.5 meters. All right, so 206 newtons, okay, would be the force required for that. Okay. Does that make sense?